Good morning and welcome back. We're going to solve the third lead code question from our must do easy questions list that we were discussing through. So this today is the time for merging two sorted lists. So let's see what they say. Okay, so this is a simple case of merging two sorted linked lists and forming a new one. They've specified that we need to splice them together, as in we can't just create a new linked list which contains the aforementioned L1 and L2, as you can see here, the ones that are arguments to this function. We have to merge them so we don't end up using unnecessary space. And that's fair. But before I start this, I want to think about what would have happened if we got two sorted arrays instead. So I think if in the case of arrays, we definitely would have um, had an easier problem because when we had an array, if we had an array, first of all, it would have been clear that we wouldn't have been able to splice the arrays together. So our only option would be to create an entirely new array. And then we would have two options. We could insert the two smaller arrays into the larger new created array with fixed end space. And yeah, and then after creating the new array with a fixed space, we would have two options. We would either insert them as their pre-existing order and then sort them, or we could insert them in a sorted manner. I think option two is better because, as we know, with the sorting algorithms in an array, we don't have much better than n log n times complexity. So if we just sorted them as we walk through the array, that would have only on times. So that's definitely a better time complexity. And obviously, the algorithm would have extra on space because we create a new array and we don't have any other way around it. I really don't think there's an easier way to solve it if we had two arrays to deal with. So yeah, just one for loop, iterate through the array, swap from the first list. If the first list's value is smaller, and increment the counter, and same for the second list. If the second list's value is smaller, and move on. That way you will have a larger merged sorted array in on time. Okay, but this is a linked list, and we'd have to return a linked list. So our solution will be completely different. But we can think like an array too in this case. Um, One way, and that is the brute force method. Again, like I said, it's the same as the first option that I discussed for the array. We could have a solution where we basically merge the lists from the get-go, and after merging them, we just sort the linked list. But as we know that like in the case of an array, like I said, that would have n log n time, and in the case of a linked list, we don't have a lot of sorting algorithms at bay. We only have a handful of options. One of the most common one of them is merge sort. So if we merged the two linked lists and started to sort them all from the beginning, it would have like at least an n log n time complexity, and that's not what we're up to. We want to do something similar for the linked list as would do for the array. We want to walk through the list, we want to walk through the list and swap the values as they come from a smaller to larger incremental way, so that we would have on time complexity. Now, in terms of space complexity, uh, we don't want to create a whole new linked list, and it's not even possible because they specifically mentioned that we have to splice it. So what we want to do is we want to swap the values between the two linked lists, and once they are in a sorted order as if they were one single linked list, we would just have to merge the tail end of the L1 to the head of L2, and then we're done. So that is the algorithm we're going to go for in this specific problem. So let's see how we can begin. So to maintain an object-oriented approach, we would want to create a swap function, which basically swaps the values as the way we want them to swap. So yeah, let's just create the function first. Swap function. public void swap. Oh, same arguments. And I might want to open up NetBeans in case I want to check over my syntax errors or other stuff like that, because LeetCode isn't really, like I said, LeetCode isn't really good at detecting every sort of error that you might do. Okay, so we have a swap function, which is not which is empty. Yeah, let's see how we can begin. We want to keep track of both the linked lists at the same time. So we're going to assume, okay, yeah, we want to take a look at the comments here. So list node, this is basically the definition for the simply linked list. It has a value, it has a next function, and yeah, that's pretty much it. Okay, so L1, so what? I think I breathed in a mosquito. Anyways, while um L1, while L1 dot next is not equal to null, and L L L2 dot next is not equal to null. To whoa. Charger to my laptop. My laptop charger to my laptop. All right. While L1.next is not equal to null and L2.next is not equal to null, that means we have values to figure out. If L1.next, wait, L1. What if the entire linked list is null? Yeah, we want to take care of that first. Okay, so if list is null, if L1 is equal to null, return L2. Because if the first linked list is null and as in it's empty, all we have to return is L2, and that's our basically sorted, merged, aka merged linked list. Return L2, and we're returning list node type, so it's fine. And if if L1 is not, if L2 L2 is equal to null, return L1. Okay, if any of the lists are null, now that we know that both of them are not null, what if it has one node? What if it has one node? Okay, so there are specific situations we have to address. First of all, if any of the lists are null, we just return the other list. And even if the other list is null, then we don't have a list, any of the list to work with. So even if we return null, that's fine, and we really don't have another option. If the second situation is we're traversing through both of the lists and one of the list ends before the other, because they don't necessarily have to have the same size as per this example. So L1 dot next is not equal to null, and L2. So this while loop will fail if any of the lists have a next have are in their last nodes. We actually want this while loop to go all the way until the end. So what we want to do is we want to create a new node to traverse it. My God, I forgot everything. So list node, this is the list node class, right? Yeah, there you go. List node current is equal to current L1 is equal to L1, and current L2 equal to L2. All right. So they have the head references, and current has been created to traverse each of the lists. Traverse each list. Okay. So while current L1 is not equal to null and current L2 is not equal to null, if current L1 dot val, we're going to assume that these are numbers because they have to be sorted, so obviously they have to be numbers, and the example has numbers, so yeah, let's just assume they're numbers. Val is great, oh, yeah, greater than current L2 dot val. That means the first list has a current value in the first list is greater than the current value in the second list. What we want to do is just put the second list's value first. So obviously when we talk about merge, the first list is going to be the first part of the sorted bigger linked list, and the second list is going to be the second later part of the linked list. So if the second list has a current value which is smaller than the first list's current value, we want to swap them, right? So this is where we call a swap function. So let's just write a comment to keep track of where we're at. So swap if second list current value is smaller than first. We want this value to be in the first list. So swap current L1, current L2. Cool. Now the swap function, what do we do? We're at a temp node, so list node temp dot val will have L1 dot val, and L1 dot val will have L2 dot val, and L2 dot val will have temp dot val. That's a basic swap function. Put it in temp, replace L1 with L2's value, replace L2's value with temp's value, which had the previous L1's value. Okay, now the swap function is done. Swap of second list's current value is smaller than first list's. However, what if the the first list's value is smaller than the second current list's value? We just carry forwards, right? So we also need to know when to traverse what. So after the swap function has been done, which one is greater now? Now that the swap function has been done, which one do you think is greater? It's going to be the current L2's value is right now greater because it was less than the current L1's dot val's value, but right now it's greater after the swap. So since this is the greater one and this is the smaller one, how do we continue from here? Which one do we want to match up the next later? Yeah, we want to continue. Okay, so as per this example, see, first we matched 1 with 1, and as we can see, 1 is not less than 1, right? So we should continue. And then where do we go? We go to the second position of the first list, and we try to compare it with the first position of the first list. That doesn't seem like it's going to have O n time complexity. Okay, so the trend is if we didn't swap, if we did not swap, then we want to move on to the larger value in this first list and check if we still need to swap. But if we do swap, as in 2 goes to the second list and 1 comes here. Um, so I think we did a slight mess up in the swap function. If we swap it normally, we're messing up the second linked list because we're not really keeping track of the second list here, and that's no longer sorted, which is crucial because we want to splice them together, right? We can't just take the nodes from here and insert it here because that's not splicing, and this is one of the requirements. If that was if splicing wasn't allowed, we could have easily taken these nodes and inserted over there and then just deleted the second list. And that's really a brute force technique. We don't want to do that. We want to specifically splice, and therefore we want to take the nodes and then replace them. But if we just like replace them normally, what happens is we're just messing up the second linked list. So if you take, for example, if you take 1 and put it over here, 2 goes here, fine, 2, 3, 4. But this 2 could have been 6, and this 4 could have been 7. Then it would have been 6, 3, 4. And I think that happens for the third value here. If you then go to the third value and you check 4 and you replace it with 2 here, then 2 comes here, so it's 1, 1, 2. So the first list is fine because that's what you're doing. You're seeing if the first list value is greater and you're swapping it every time. But the second list gets messed up. So what we want to do is when we swap it, we also want to check if we're putting the value inside the second list in the right position. So we also want to traverse the second list. So while L2 dot L is current L2 dot L. So we already know that the current L2 dot val is less than the L1 dot val. So that's why we took the L1 dot val off and we put it L2 dot val there, val's value there. But what if the next value is also less? So while L2 dot next is not is is also less than temp dot val. There you go. Okay. So what this does now is we take L1, which is the greater value, put it in temp, and then we take the lower value and put it in L1 so that L1 remains sorted. And then we take the temp value and we just don't put it where L1 was, where the old value was, because that might mess up the second list. So we put it until we reach a value which is actually greater than the value which we're trying to insert. So until then we have to traverse. So L2 dot L2 L2 dot next. until L2 dot next is actually less than temp dot val. So let's say we're trying to well, this was 114 and this is 234. So all of a sudden L1 dot val 4 is greater than L2 dot val, which is 2. So we want to replace them. So 2 comes up here, but we have 4 at hand. So we don't just put 4 in 2's position. We check. Uh, while L2 dot next, which is 3, is less than 4, we traverse. And then 4 is not less than 4, so we go and we replace. Oh, that way we're losing 3. Okay, so we actually want to insert it in 1's position because that's where the 4 belongs. But then we have to sort it. So 4, 3, 4. And then while L2 dot next is less than temp dot val. So if 3 is less than 4, so next what we want to do is actually sort the second linked list because that gets messed up every time we try to swap. So, okay, so the value from the first linked list is now in the second linked list, but it's not in the correct position because let's say we took out 4 and put in 3 here. Sorry, we took out 4 and put in 1 here. So now it's 4, 3, 4, as in this example. So we want to push 4 back. Um, so how we do that is we know that temp.val has our 4 and L2.val also has 4 in the incorrect position, and we just want to swap it once the correct position is reached. So what we want to do is while L2.next.val, that is the next value, is less than the value that we have, change L2. Actually, we don't want this line here because we don't want to put it in before we swap it. So change in L2. So L2 goes to 3. And then, as per this example, L2 goes to 3. And then, again, it tries to take in L2.next.val, which is 4. And it's not less than temp.val, which is 4 too. So it falls out of the while loop. And L2 is at 3, while temp.val just has the value, right? Yeah, we also want a pointer here at 4, so we'll keep this line and then actually use something else to traverse it. So this node, current node, L2, current node.next.val is less than temp.val, current node is current node.next. L2 is at 4, current node stops at 3, so we want to swap the values. Oh no. Yeah, we don't want to swap it because then that still messes up the ordering. We want to push it backwards. What am I doing? Okay. sort. Yeah, we want to swap the values every time. So L2.val. I don't know why this took me so long. L2.val actually becomes L2.next.val and whoa and temp. So as you can see, L2.val has temp.val. Now, if let's say we pushed in 2, so it's now 235, 234 in the second linked list. Now, if it's not null and it's not null, the next node has a value, and the next node's value is not less than temp.val, as in it was greater than 2 because it's 3 the next node, then this while loop won't be executed at all. But if it's actually less than, if the next value is actually less than the current value, which is, let's say here we have 5, then it will be executed. So what happens then? L2.val is equal to L2.next.val. So 5 actually becomes 3. So now we have 334, but we have 5 in temp 2. So then L2 is equal to L2.next. We move to the next one, and then we change the value to temp, and now it's 354, right? And then we iterate it again. L2.next is not equal to null, true, and L2.next.val is less than temp.val, true again, because temp was 5, so true again. And then L2.val is equal to L2.next.val, so 5 becomes 4, temp is still 5, so this becomes 144, sorry, 344. Then L2 is equal to L2.next, and L2.val becomes temp.val, so then it becomes 345. We fall out of the loop, and the swap function has been completed, both for thus sorting the second linked list and also sorting the first linked list. Okay. Now, current L1 is not equal to null, and current L2 is not equal to null. We swap if and only if second list's value is smaller than the first. If it's not, we continue. And after swapping, we go back to this, and we still have current L1, but we move on to the next value in current L1. So current L1 is equal to current L1 dot next. And then we compare 2 with the smallest value on the second linked list. Okay, cool. And we continue this until only the first linked list is exhausted. So then it's done. Now, did I miss something out? Let's see. If the lists are null, we return the other one. If both of them are null, well, we have nothing to return. We can just return either one. Then to traverse lists, we conform these nodes. and we traverse every time until we exhaust the first linked list only. We traverse all the way until the end of the first linked list, and every time we traverse, we check if two, let's say if the current node in the first linked list is less or greater than the second linked list. If the second linked list has a smaller value, well, that will be swept. So the smaller value comes into the first linked list at the specified position because we're uh, traversing through sorted linked lists, and the first linked list already automatically becomes sorted, and um, the value that goes into the second linked list is sorted in this swap function here. How? The sorted linked list on the second linked list, to sort it, we traverse it all the way until it's null. And or let's see. Or we traverse it until it's null, or we traverse it until the next value. We traverse it as long as it's not null, because if it's null, it needs to fall out, or we traverse it as long as the next value is less than the current value. Every time we push, every time we push the temp value into the specified position. This line is not really necessary here, but I'll keep it nevertheless. And that's basically it. Now, obviously, the runtime for the space complexity is 01 because we're not creating a new linked list. Oh, it's not done yet. We have to splice it. I forgot to splice it. Okay, let's splice it then. We have to merge. What this does is this while loop will sort the linked lists in a way where we have, if they were spliced, if they were merged, then we have a merged version, right? So where does current L1 stop? Current L1 automatically after the entire traversal becomes the tail of the first linked list, and we already have the head of the second linked list using L2. So we just have to make sure seeing if the traversal is right here. So let's see. We stop after it becomes null. Is that right? If we put a dot next here, then the last value won't be swapped. Well, we need another if statement here. So if current L1 is not equal to, sorry, current L1 dot next is not equal to null, else Okay, so what we want to do is until current L1 is not equal to null. This should have been a do while loop actually. Okay, let's convert this to a do while loop because we want to run the test cases after the swap has been made, not before. So do while, the while should be dot next. There you go. I don't like using break statements, that's why I'm converting it to a do while loop. And I'm gonna copy this code, put it here, fix the indentation. Oh my god, I'm hitting 36 minutes. Should have been done within 30 minutes. That was the goal, despite the fact that I've just begun. These are easy problems, shouldn't take that long. Anyways, I forgot do while loop syntax. I do have NetBeans, so I can check, but still. Whoa, man, I'm talking about Java. This took too long. Do while, no spaces. I really don't think space matters, but whatever. Okay, so first, clearly L1 and L2 are not null. They have the first node at least, so we want to do something. We want to check if current L1.val is greater than current L2.val. We swap. Okay, if it's not greater, then we continue down the road. So after swapping, if current L1.next is not equal to null, then and only then we convert. And after traversing, we check if current L1.next is not equal to null before traversing it again. Hmm. What? Well, a do while loop really doesn't make sense here because all it does is it just makes sure that it happens the first time. I'm trying to make sure that it happens all the way until the end. Let's see. Okay, still have the while loop. Okay, so current L1. Okay, so we're gonna break the loop the moment the last node is. We have a break statement here. I really can't think of a better way to do this, but the the moment we have hit the last node, it's still not going to. It's still going to satisfy this condition because this is the last node, so it's still valid. We're gonna swap it, and then since next is null, we're going to break. Next is null. This is not going to operate, so we're gonna break away from this loop and current L1 is after that current L1 is sorted and current L2 has already been sorted by you writing this little function here in the swap function. Now, all we have to do is splice it. So current L1 is clearly the last node and L2 is the head of the first node. So current splice, current L1 is equal to, sorry, dot next is equal to L2 and we're done. I mean, we should be. Now, let's discuss the solution a little bit. There is O1 space complexity. We didn't write this to be out of space, so it's fine in terms of space. In terms of time, the other option that we could have done is we could have just spliced it at the very beginning and then used merge sort the common sorting function for linked lists, but that has an O n log n time complexity. Since we already know that both of these lists are sorted, what I wanted to do is just check the first value of the L1 and first value of the L2 and swap if necessary. And every time we do swap, we push it back to the L22 to maintain sorted to maintain the sorted feature of the L2 linked list. And L1 is already always being sorted because we only swap if it's the bigger version of the number. So that's my solution. It's not supposed to run because I didn't run this through NetBeans, so highly unlikely, but let's see what happens after 41 minutes. Wow. This was clearly a 15-minute question. I need a lot of ground to cover. Okay, so we have a problem. Current L1.next is equal to L2. Where is this? Line 44. Oh, sorry. It should be small l. Let's run code again. Then this L2. Oh, I used large L's in a lot of places, it seems. Let's see, where's line 55? L2.next is not equal to null. I also want to check the last node too, so. Okay, so if L2.next is equal to null, so let's say L2 has one node, okay? Or if we're at the last node, let's say. And L2.val has already been given to L1.val, and then L2.next is equal to null, we fall out of the loop, so that's fine. And then L2. I'm just checking this over again. I know I fixed the error. L2.next.val is less than temp.val. Yeah, the next value is actually less, so we need to swap them, and we do. Cool. Cool. Okay, perfect. Let's do this again. Missing return statement. Where's the return statement? Oh yeah, we need to return L1. We need to return L1. Return L1. And current L1.next. Yeah. Oh my god, so many errors. Temp.val is equal to L1.val. What you saying? Variable temp may have not been initialized, but I did initialize it. So what's the problem? Let's note current L1. Okay. Oh my god, we need to initialize them. Yes. Okay, we're actually. I forgot how to code completely. Let's see how to create a new node. Node 50. Okay. New list node. Okay. Okay, so this is L1, this is L2. Yeah, temp needs to be a new node because it needs to hold the value while we make changes to L1 and L2. Okay, so temp needs to be new, but current doesn't need to be new because we're just traversing current, so it doesn't need to be new. L1 has the head reference. Current is the one being traversed and changed around to make permanent changes to the linked list, but temp needs to hold the value temporarily, so it needs to be a new list node. Okay, and then now the error is, all right, need to call it. I completely forgot programming. Null pointer exception. This should be and. The next one can't be null, and the next value, once it's not null, has to be actually less than the temp.val to have to change. Got my conditions wrong. Okay. All right, so now it's accepted, but I want to make this a bit faster if possible. The list that we randomly chose current L1 to be traversed, but we really want to traverse through the list which is smaller and merge it with the larger version, right? Yeah. So, is there a way to find out the length? Well, there's no way to find out the length of a linked list, so that's not an option. Okay, so we really randomly have to choose. We really don't want to find out the length anyways and then get the shorter one so that we can traverse the shorter one, because if you want to find out the length, you'll have to traverse it anyways, so it's not possible. Anyways, L1 is going to be, yeah, these test cases are fine, and then we traverse each of the lists. Every time we traverse, we swap it, we sort L22, and then at the end we splice, and then we return the head of L1. We created a new node here to hold the value temporarily, but everything else is fine. So let's submit the code and see where it happened. In terms of time complexity, um, yeah, since we're, like I said, since we're basically swapping between two sorted lists, chances are we don't have to go through the entire list every single time. So even though seemingly we have to even though it seems that we have to iterate through n by 2, as in the number of elements in the first linked list, and for each of those iterations we might, worst case scenario, we might have to push the swapped value all the way to the end of the second linked list, even though that is a possibility, because there might be separate combinations which are really highly unfavorable based on the code that I've written. um, it's still unlikely to happen more often than not. So it's not going to be O(n) squared. If anything, it's going to be a very, very amortized version of O(n) squared time complexity. So I expect it to be better than the merge sort implementation. Okay, so let's submit it. All right, average runtime 1 millisecond faster than 44.81% Java all in submissions, and that's it. Okay,